Hi everyone, thank you for joining me today. My name is Daniel and I work for Google on a project called Spanner. Like many of you, I have been working from home from New York since the start of the pandemic. And it has been fun to have my wife as an office mate for a change. On the other hand, I've had to contend with my cats trying to join every meeting I have. So hopefully they won't try and join us today. What I would like to talk to you today about is how Spanner manages order and consistency at Google scale. Spanner is Google's SQL database of choice. We serve hundreds of millions of requests per second, manage exabytes of data, and we have over 30,000 production databases today. But Spanner was not actually Google's first database. Spanner was born out of a previous database called Bigtable, which mostly focused on storing data to one single geographic location. Contrasted with Spanner, which is able to synchronously replicate information across multiple locations, thereby improving our redundancy against single failures. But like Bigtable, Spanner continues to be horizontally scalable. The way Spanner does this is we take our data range and we divide it into shards. And for each shard, we replicate the data among the different machines using something called Paxos, which is a consensus algorithm that allows us to make sure that these multiple machines all stay in sync and agree on what data they should have. However, while that might be the most famous thing that Spanner is known for, what I want to talk to you today about is consistency. When you take a database and you distribute it across multiple machines like this, one of the problems you often run into is that data across different machines may no longer be consistent. To give you an example of the problems you might face because of this, in a database, it's pretty common to have something called a secondary index. In this case, I have a table of songs, and their primary ID is just a random integer called the song ID. But it's often useful to be able to look up a song by its song name. To make this lookup efficient, this is where a secondary index comes in, because we could create an index on the song name, and now our song name index is organized by the song name, and we can do these song name lookups very efficiently. In Spanner, it's not uncommon to have the index table and the base table live on different machines. When we insert a row into the base table, we also correspondingly insert a row into the index table. It's interesting to note here that even though there's really only one logical song, we now have it represented in two different places in two different machines. This is where the consistency problem comes in. An obvious one would be, maybe we put in the new song row, but the index machine is not up to date yet. When we scan the index to look for songs, we might not be able to find this new song we added. An even more insidious problem is, in SQL databases, the SQL optimizer is allowed to use the index as it pleases to make the queries go faster. That's the whole point of the optimizer. So in this case, we're trying to look up a song by its song name, but the property we're trying to retrieve is a column that's not found in the index. So what we actually need to do is go to the index, look up the song ID from the song name, and then go back to the base table and try and look up the original song row and look at the column we need. If the machine that hosted the base table was slow or lagging behind, we might find that we can't actually find the original song row, even though the index has it. This is problematic. We could just drop this row, but thinking of all the different edge cases you might have to handle because of a lack of consistency can quickly become mind-boggling. So in Spanner, we strive to provide one of the strictest forms of consistency called external consistency. And this really boils down to two different guarantees. The first of which is something called serializability. Even though Spanner might handle thousands of transactions concurrently, the result of these transactions executing concurrently is indistinguishable from when, if you have a single machine with a single thread processing these transactions one by one, there is some ordering in which you can put these transactions such that you get the same result. External consistency also means that the transactions serial order in this single-threaded, single-machine model has correspondence to actual real-world time. This allows users to see, like, I did transaction A, and then I did transaction B, and the ordering we see on the database would reflect that. Why do we pick such a strict consistency model? Well, it's what users intuitively expect. Many people are familiar with the single machine, single thread, zero transaction execution model. And even though Spanner is a distributed database, this simpler model is still very much what they are used to reasoning about. And weaker consistency actually do lead to errors. Earlier in my software career, I was tasked with writing a portion of the program that had to uphold the following invariant. Writing to the submissions SQL table, we want to make sure that every user has at most one submission. So I did the obvious thing. I counted how many submissions the user currently had, and if the user had 0 transactions, then sure, I would go ahead and insert into the submissions table to add one new submission for the user. I was even really proud of myself that I remembered to wrap the whole thing in a transaction. Unfortunately, I later discovered, and spent many hours fixing, that this was not sufficient. Most databases use a weaker consistency model that allows for a second transaction to come into the middle of my original transaction and add in a new row to the submissions table. When this happens, once the 2 transactions finish executing, you now find that your submissions table has 2 rows, which broke the invariant I was trying to uphold in the first place. A different kind of error that can happen under weaker consistency models is something called time travel. Let's say I write to the database and I set the value of A to 1. And then in a separate transaction after that, I set the value of A to 2. If time travel was allowed, it's possible for this later transaction in time, in terms of the database's point of view, to be ordered before my original transaction. Now, when I go to read the value of A, I find that the value of A is confusingly still 1, and will always be 1, because the right to change it to 2 got ordered before the right to change it to 1. This is highly confusing, as you might expect, and maybe a little bit of an extreme example, but there are other, more subtle forms of the problem that can be equally confusing to users. For example, maybe I write the parent node first, and then I write a child node in a separate transaction after that references the parent node by ID or by name. If this second write time traveled before the parent node write, similar to this example, when I go read a child node, it's entirely possible that I won't be able to find the parent node. And again, this would be totally confusing to an application developer. And at Google scale, we find that eventually all such anomalies will be encountered. And they are extremely painful to fix because not only do you have to fix them, but even debugging and trying to prove under these weird, loose consistency models how this actually might have happened is difficult. And we once saw a developer spend a month trying to craft the right sequence of steps under all different kinds of loose consistencies to make sure that the right result would happen. In some sense, this is kind of like premature optimization, where you are trying to make your code performant under weaker semantics in the hopes of better performance, when in actual fact, for 80% of your code, maybe that didn't really matter. So instead, what we decided is we want to make correctness as easy as possible. And then for the remaining 20% of the application that's super performance critical, provide escape hatches to allow users to get better performance, but at the trade-off of weaker semantics. This shows in the default settings when you do a read against Spanner. By default, you get what's called a strong read. This strong read is guaranteed to get the latest version of data from Spanner, and in particular, this latest version will be consistent with all the previous transactions that executed and committed before you started this read. For our power users, we offer 2 weaker forms of reads called exact timestamp and bounded staleness. What these reads do is they read data slightly further in the past. This allows Spanner to respond to the read faster. But a crucial thing is that transactional guarantees, transactional invariants that were maintained continue to hold. It's as though you just went back in time a little bit at the database and looked at the state of things, as opposed to totally impossible combinations of data happening. I was being a little bit glib earlier when I said, Users expect external consistency, so we should give it to them. In actual fact, if external consistency was really expensive, we would just throw up our hands and say, I'm really sorry, but it's too expensive and we can't give it to you. So the trick is, can we make external consistency cheap enough? Our observation was that many workloads are read-heavy, and so if we made read-only transactions cheaper, then maybe external consistency would be a workable idea. To help explain to you how Spanner achieves this, let's step back for a bit and think about how Spanner reasons about transactions. In Spanner, transactions become visible according to what is called their commit timestamp. When you commit a transaction, every transaction is assigned a timestamp by which you can pretend that all effects, all writes, all reads that you did for this transaction happened at exactly that point in time. And the relative visibility of transactions that come before or after you are determined by your relative ordering in commit timestamp. Going back to our external consistency requirement, you can translate this into the following requirements on commit timestamps. Any transaction that starts after a transaction that has finished must get a greater timestamp, because this then guarantees that our later transaction will be ordered in transaction commit timestamp space after the original transaction, matching the wall clock order in which we did these transactions. One way to satisfy this requirement would be to assign each transaction the current time between when you start the commit request and when you finish the commit request and return it to the user, because this naturally satisfies this ordering property we want. However, a more astute person would notice that clocks are not reliable across machines. Let's say, for example, we have two machines, machine A and machine B. If machine B's clock is slightly slow, what if you commit first to machine A in transaction A? This gets assigned a timestamp of 100. We then go to machine B and commit transaction B. Because machine B's clock is slow, it might assign transaction B a timestamp of 99. This violates our ordering guarantee because even though transaction B started after transaction A finished, going by the commit timestamps, the reverse is actually true. Transaction B comes before transaction A. So that's not going to work. What we did is we invented a service called TrueTime. TrueTime allows us to synchronize a global notion of time between all the machines that run Spanner. In essence, it provides an interval, TrueTime earliest to TrueTime latest, in which we can be very certain that time is contained within that interval. And to give you a notion of how tightly we've managed to bound this notion of time, the average interval width in production today is less than 1.5 milliseconds on average. So it's a really tight notion of now. This allows us to piece everything together and provide lock-free read-only transactions, which is exactly how we provide cheap reads to Spanner users. What we observe is that a read-only transaction must observe the effects of all transactions that commit before the read-only transaction starts. Translating that into commit timestamps, the read-only transaction needs to see any transaction with a commit timestamp less than now. And again, we don't know what now is precisely, so to be safe, we pick TrueTime latest as now, because this guarantees that we will see all transactions that happened before this transaction starts. When we go to a particular replica to read the changes, it's possible that this replica might need to wait to guarantee that it will have seen all the changes that are relevant for this particular read timestamp. But otherwise, it requires no transactional locks and will never abort. And this is pretty nice because then we don't have to worry about retries or regular reads due to lock conflicts and other types of aborts that you might see otherwise. In essence, this is how we provide the cheap reads for our users. Going back to my original example about secondary indexes, when we inserted the row into the base table, in the same transaction, we would also update the index to maintain consistency. Since they're part of the same transaction, they both get assigned the same timestamp. And for example, let's assume that this transaction committed at timestamp 5. Now, when we go to read the index in our earlier example, let's say the read happened with a read timestamp assigned that was greater than or equal to 5. Because we have been able to order our data across different machines, when we read from the index table or from the base table, we are guaranteed to observe the effects of this earlier write because we say that, hey, I must see any write that finished with a timestamp of less than 5, which includes the write we just did, thereby eliminating the problem we ran into earlier. Conversely, if you did a stale read and read slightly in the past, because we say, hey, we only want to see any transaction that committed before or at timestamp 4, this latest write would be elided from both the index table read and the base table read, maintaining our consistency between the two views. Let's talk about a more advanced usage of Spanner. Zanzibar is Google's global authorization system. They use Spanner to store what's called access control lists that mediate access to various objects. For example, the fact that I, Daniel, am able to access this slide deck you're seeing was probably mediated by Zanzibar. Zanzibar is an extremely low latency service. They aim to finish 95% of their checks within 10 milliseconds. And they're a pretty big user of Spanner. They do about 20 million reads per second to Spanner. For them, the main problem that they're trying to prevent is what's called the new enemy problem. And it boils down to making sure that they respect the ordering between when you change the echoes on an object and when you update the content. For example, let's say Alice wants to temporarily remove Bob from being able to view some slides. Alice goes to Google Slides and says, hey, remove Bob. Google Slides goes to Zanzibar and says, please remove Bob from the echo set, and then writes it to Spanner. Alice can now tell Charlie, hey, please go ahead and make the changes. I've removed Bob. And so Charlie will update the content, and the Google Slides service will check with Zanzibar, is Charlie allowed to modify the content, and finally write the updated content to the storage. Now, when Bob comes along and attempts to read these updated slides, Google Slides will check with Zanzibar and say, hey, is Bob allowed to access these slides? And Zanzibar will probably go read from Spanner and check and say, oh, Bob is no longer in the echo set because it's been updated and therefore reject the request, preserving this desired notion of echo ordering updates and content updates. If instead Spanner did not have external consistency and was allowed to return stale results, Spanner could have returned an older version of the echoes that still had Bob in it, and then we would wrongly allow Bob to see the latest content changes, even though Alice had already removed Bob before Charlie went to make the update. So strong Spanner reads would suffice for Zanzibar's correctness requirements. Unfortunately, these strong reads are not sufficient to meet their latency goals. In sense, Zanzibar is a global system. If you make an update in one side of the world, it's really hard for this notion of the update to propagate to the other side of the world in under 10 milliseconds, their latency goal. Speed of light and information just does not travel quickly enough. Luckily for Zanzibar, they've decided that they are okay with returning slightly stale echo check results. This allows them to do reads slightly further into the past, and therefore obviate the need to wait for information to propagate across the world. But critically, they still need to be able to respect the causal ordering between echo and content updates. How do they do this? What they have introduced is the notion of a Zuki, which is an opaque consistency token that clients can use to help preserve this desired ordering. This Zuki essentially contains just a Spanner timestamp. And when a Zuki is supplied, it tells Zanzibar to say, when you read from Spanner, make sure your read is no staler than what is specified in the Zuki. And how do we use this? Let's go back to our previous example. Alice removes Bob from Google Slides. Google Slides then goes to Zanzibar and says, hey, please remove Bob from the echo set. And this gets written to Spanner, and Spanner assigns the transaction a timestamp of 1. Now, when Charlie updates the content in Google Slides goes to Zanzibar and says, hey, is Charlie allowed to modify this content? It will then go check with Spanner the echoes with regards to Charlie. But critically, as part of this check, Zanzibar returns a zoo key to Google Slides. This zoo key contains a timestamp that will be then used to bound any future checks against the content to make sure we see all the latest echo changes. In our case, we know that the last change to these echoes for the slides was done at timestamp 1, so any value greater than 1 would suffice. When Google Slides then goes to store the updated content, it also stores this zoo key from Zanzibar alongside the content. Now when Bob comes along and tries to read the slides and the updated content, Google Slides will retrieve the content and the zoo key from storage. The zoo key is then passed along to Zanzibar, who then knows that when I go read from Stepbanner, even if I use a stale read, I need to make sure that this read is done at a timestamp greater than or equal to 1. This guarantees that Zanzibar will see any echo changes that happened before we had modified the content. By doing so, we preserved the ordering desired between echo changes and content updates, as described earlier. What I would like to advocate today is to make correctness easy. We should strive to give our users of our systems intuitive semantics, even if that requires some extra work on our end to make sure that we can provide these semantics with enough performance that for most users, this will be fine. However, we still need to provide escape hatches for our power users. These users have very extreme performance demands, and sometimes it's okay to relax the consistency semantics for a small set of their use cases so that they can meet what they desire to achieve. With that, thank you for joining me today, and I hope you found this presentation useful.